In this video then, we're going to run through a nucleophilic substitution question. I appreciate that spoils the name of the mechanism there, but this whole thing's on nucleophilic substitution. It's another mechanism at A level. Again, it's an AS level mechanism, and as I probably mentioned before, these mechanisms never change. They're so straightforward. All you got to do is remember the arrows and remember where to apply them. This is the main bulk of it. So I'm going to choose one question to work through here, or just the one. It doesn't need to be long-winded because, as I've said, these mechanisms are always the same. So I'm not going to keep doing the same question over and over again. I'll just do the one, just to highlight a few little pitfalls with how this mechanism works. So we've got a question then. Allyl bromide reacts with aqueous sodium hydroxide. Outline the mechanism. Standard A-level question. So the first thing I would do here is just draw it out, just to get the gist of what's going on here. So you've got carbon to carbon double bond, you've got H2 on the one, and you've got what looks like another H, and then a carbon, hydrogen, bromine. So allyl bromide, you've got 3 carbons, 4 hydrogens, and a bromine. There you go, that's nice and straightforward. Now, you're reacting with aqueous sodium hydroxide. So this is the first little test really, because we're adding an AOH. And the reason I picked this question is because there's 2 choices here. Okay, there's 2 mechanisms this could be. Now, obviously, we already know which one it is because I've told you. But if you looked at this straight away, you might be, correct in pointing out, well, hang on, there's a double bond here. Now, this double bond could mean it's electrophilic addition. And that would be a different mechanism to what I'm just telling you. We've got this carbon-bromine bond, which also is something you could do for nucleophilic substitution, but which is it? Well, the answer to that comes in your reagent, your NaOH. Now, NaOH is ionic, okay, because you've got Na, when you put it in water, you form essentially Na plus and OH minus. Okay, it's an ionic substance. Now, is sodium an electrophile? No, well, not at A level anyway. Okay, you're not going to be using Na plus to attach to a carbon. Okay, we're not attaching group 1 and group 2 metals to carbons. Okay, that we're not using Grignard reagents. Okay, we're not doing that. This isn't degree level. We don't do that. Okay, and at no point will you ever be bonding a sodium to a carbon. Okay, at all. Okay, with a covalent bond, it ain't happening at A level. So immediately, as soon as you see a metal here, it should immediately rule out electrophilic addition. Okay, it's not going to be that. We're not touching this double bond with a 10-foot barge pole. It's going nowhere. What we are using is the OH minus. This is a fantastic nucleophile because it's negatively charged, and in solution it has a lone pair of electrons it can easily, place into, can use. Well, I can't get my words out. It's got a lone pair of electrons it can use to kickstart the mechanism and replace the bromine. So how do we draw this then? This is always drawn the same way. So we're going to ignore the double bond. I don't care about the double bond. It doesn't matter to me one bit. I'll draw it anyway. But that's not going to be touched. Okay, we're not going to touch this at all. Okay, I'm just going to put this in here. That bit is irrelevant. The bit that I'm interested in is this end bit here, this CH2 CBr. Now that's the really important bit. Now, as we mentioned before, okay, in other videos, dipoles are really important. Okay, electronegativity is important, and on this carbon to bromine bond, bromine being more electronegative than carbon means we have a delta negative and a delta positive. Make sure you label these. Okay, if you don't label them, you run the risk of losing a mark. You must label them. Okay, it's not me being pedantic, it's genuinely a marking point. So it may seem like a bit of extra work and it's always obvious. It doesn't matter. Examiners are idiots. Tell them exactly how it is. Right, the sodium's irrelevant. You can ignore that. Okay, for this mechanism, you can just ignore the sodium. Okay, we can just put in the OH minus. Now, nucleophiles OH minus, when you draw it, it should be OH minus with a lone pair of electrons. The lone pair of electrons should be on the oxygen. Okay, so just be wary of that. And all we're doing is substituting. Now, substituting is very, very straightforward. We're adding the OH minus and we're taking off something else. The thing we're going to take off is the bromine. Okay, so we're going to get rid of the bromine and we're going to add on the OH instead. So that's why it's a substitution mechanism. One goes in, one goes out. Now, where does my arrow go? Remember, electron pair movement is shown by arrows. So we're going to start the arrow where the electrons are and finish where they're not, or where we'd like them to be. Now the electrons, hopefully, the OH minus has got a big negative charge and a lone pair of electrons. Hopefully this is screaming out to you that this is where the electrons are, and we're going to put them to a positive charge. Now, the positive charge is where the carbon is. That's a delta positive. It's not a full positive, but it's a partial charge, and it's an area of electron deficiency. So we're going to put that there and effectively form a bond between the carbon and the oxygen, which makes perfect sense, because that's how you make an alcohol group. So start our arrow at the pair of electrons, curl it round, stick it in there. Now we can't just stop there because carbon would have 5 bonds, so now we have to get rid of the bromine. And we do that by breaking this carbon to bromine bond. So again, to break the bond, we start the arrow where the electrons are. Now the electrons are in the center of the bond. So start the arrow here, up and down, nice bit of curl there, and that's it. And that's the same every time. This never changes. Okay, for nucleophilic substitution, you start with the nucleophile, arrow into the carbon, kick out whatever you're getting rid of, and that's it. You're done. Okay, and that it is that simple. Okay, there are no tricks, there are no traps. That's all it is. Okay, and if I draw the product now, it's going to just be what you'd expect. The OH comes in, it's bonded, the H's are there, and we've got Br minus floating around. Now, that's all you need for the 3 marks, by the way. This is all we need. If you wanted to wonder, well, how can you have bromine floating around? Remember this sodium up here from earlier? Yeah, that's still there. And as a final step, you do not need to include this, by the way. It will not be on any mark scheme. The bromine gives its electrons to sodium, and you make NaBr as a secondary product. Okay, but that's not important. That's not the important bit. That's not part of the mechanism that you need to know. That's just a sideline if you wonder where the bromine goes at the end. Bonds to the sodium, forms NaBr. Okay, in terms of exam technique on this, again, make sure you put the dipole in. The arrows, again, the arrow can start from either the lone pair on the oxygen or the negative charge, but nowhere else. So please do not put it from, here you go, I get my red pen out. Let's get the wrong pen out now. Okay, do not do this or this. Okay, wrong. Don't do it. Okay, keep it simple. Okay, these mechanisms are not designed to be complicated. Okay, they're meant to be very, very straightforward representations. So just 2 arrows is all it is. That's it, total. The total of this is 2 arrows, and it's always the same 2 arrows. So that's it then. There's 2 curly arrow mechanisms at AS level. This and electrophilic addition. In total, there are 5 arrows. Okay, this is not complicated to learn. Okay, and again, it's about look, cover, write, check. Do it again and again and again until you cannot possibly get it wrong. And of course, name the mechanism nucleophilic substitution. And that's it. So there you go. Quick little one on nucleophilic substitution. I'm not going to do any more because they're all the same. All these questions are identical pretty much. They might use different nucleophiles, but the arrows never change, and the rest of the compound is irrelevant. So it doesn't matter what's over here. Okay, it doesn't matter what, this could extend on and on and on and on. Doesn't matter. The only bit we're interested in is this bit here, and that never changes.